Hello, welcome to our channel again, Suraj here. And today, finally, we are going to discuss about the Planck radiation law. So, in the past few lectures of the Blackbody radiation, we have discussed about the Rayleigh-Jeans law and the derivation of the Rayleigh-Jeans law. That how we can find out the number of the standing waves in a given particular frequency range or in a given particular wavelength range. How we can find out have done in the Rayleigh-Jeans law lecture. So you can watch out that particular lecture. And in today's video, we are finally going to the Planck radiation law, which is a very good approximations of as the black body radiation curve, as you can see that. And we are going to discuss that how exactly Planck introduced the idea of the discrete energy and how the discrete energy formulation solves the problem of a particular black body radiation curve. So let's start our today's lecture. So as you can see that I have made a comparison between the classical and the quantum radiation curve graphs. It means what's in the classical and what's in the quantum. So as we can see that in the classical, the equipartition theorem, which I have discussed in the previous video, that each energy assigned to the given degree of freedom, suppose that the particle is moving in the two dimension, so the average energy in each of this particular, let's say this is 2D dimensional motion, so the average energy is equals to, in each of the degree of freedom is equals to 1 by half kT, and that is the classical equipartition theorem. And this equipartition theorem, yes, this equipartition theorem is wrong when we deals with the high frequency. Yes, and that's why we have to introduce the concept of the quanta, and that's where the quantum mechanics start. How? So as you can see that if I here write down the formula of the Rayleigh-Jeans law, which is the number of standing waves in a given frequency range d mu is equals to 8 pi mu square divided by c cube, and here it is kt d mu. So this is the formula of the energy density, and within a particular number of standing with energy density for a given frequency range d mu, and this is the general formula. But here in this particular graph, it is the emissive power, and here is the energy density. But no worry, we are mostly going to deal with the energy density than the emissive power. This graph is just for the explanation to understand that how the curves look like. And here, as you can see that the energy density, which is energy per unit volume emitted by the blackbody radiation within a frequency range d mu is equals to 8 pi mu square divided by c cube kt d mu. So here the whole problem is with this. Remember, in our previous lecture, we have discussed that how I can find the energy density or energy per unit volume in a given frequency range. So if you remember, we have derived the number of the standing waves in a given frequency range, and the number is exactly equals to 8 pi mu square divided by 1 minute divided by c cube d mu. Okay, and this is the number of the standing waves in a given frequency range d mu. And if we multiply out this particular expression with the average energy of each of the standing wave, which is kt, it means multiplying kt on both sides. Here we also have to multiply kt on both sides. What we get? So generally this is per unit volume. Okay, energy. Okay, so this is NVDV. It means the number of standing waves per unit volume in a given frequency range is equals to this. And if I multiply it by the average energy, you will get this particular expression. It means the whole concept here is that we have to multiply it by the average energy of the each oscillator. But here the energy of the each oscillator is wrong. It means we have to do the correction in the each energy. It means the average energy. It means in the equipartition theorem. And that's where in the quantum, if you introduce the concept of quanta, the average energy, or you can say that this equipartition theorem is equals to average energy is equals to h mu upon E to the raised to the power h mu divided by kt minus 1. So this is the equipartition theorem in the quantum mechanics, or you can say that at high frequency. And that's the problem with it. It means what the Rayleigh and Jeans had done, that they just multiply it by the KT, because at that time they do not know that there is also a different equipartition theorem for the high frequency, and that's why their law is very inaccurate. Because as you can see that in this particular law, the energy density per unit volume is directly energy density is directly proportional to the mu square, which means frequency square. But this is not the case. According to this particular graph, according to this particular graph, or let's say this is lambda graph, you can change this particular graph into the frequency also. So if I made here another graph of the energy density u mu, and here for the frequency, then the graph should look like this. It means it goes to zero at infinity. It means the frequency has to be zero at infinity. But according to the classical idea, according to the Rayleigh-Jeans law, this is not true. The energy goes to infinity. When you plug the value of mu infinity, the energy density also tends to infinity. But that is not true. As you can see that in this particular graph, if you increase and increase the frequency, it means intense. If you increase the frequency to infinity, it should be zero. But the classical idea is like that. It is the graph which keeps increasing and increasing till infinity, and that's the problem with the Rayleigh-Jeans law. And that is arrived, and that why the problem arrived. This problem arrived because of the equipartition theorem. So in this particular lecture, we are going to derive out the this particular law, which is this particular average energy is equals to this, because if you put the frequency infinity, you have to make an equation of the energy that the average energy should go zero at infinity. When you put the frequency infinity, it should be zero. And that's the thing that this particular equipartition theorem is predicting, because if you put the value of mu as infinity, if the mu tends to infinity, if mu tends to infinity, it should be zero. As you can say that here, if you put the mu infinity, see this particular thing. If you put the mu infinity, then h mu upon kt also tends to infinity, and infinity minus infinity is infinity, and the average energy is equals to h mu divided by infinity, and you know that 1 upon infinity is 0. It means average energy is 0, and that quite well agrees with the graph of this particular energy density and the frequency graph. But in the classical idea, as you can see here, if you keep increasing the frequency, the energy density also increases. But here in this particular case, it is not true. If you keep increasing the frequency, or you can put down the value of frequency as infinity, the average energy is zero, and that's what we have to do. Now, hope that you understand that why there is a need of the another equipartition theorem, and why this classical equipartition theorem is predicting something which is very, very wrong. And that's the way the idea of the quanta emerged in the quantum physics by the Planck. So now we are going to derive out this particular formula. So let's start deriving this. So let me write this a Planck postulate. Okay. So Planck postulate was like Planck postulate. Okay. E is equals to nh mu. It means the energy emitted by this oscillator. What I mean here, if I saying oscillator, so here the oscillator is the electrons. As electrons are moving and moving and moving, so we will treat the electrons as oscillator. So the energy of this particular oscillator is only in the discrete fashion, not in the continuous fashion. Not in the continuous fashion, we have to put this energy as nh mu. And that is the consequence of the Planck postulate. What Planck did that, he just uses the discrete energy, and using the discrete energy, he derived the average energy formula. Because if you have studied the statistical physics, you all know that the average energy is equals to the integration from 0 to infinity E, probability of E, dE, and divided by integration from 0 to infinity of E, 0 to infinity P E D. So this is the formula for finding the average energy of the Planck, or you can say the average energy of any of this particular degree of freedom, and that exactly came out to be 1 by half kT. What Planck did that, he do not do the integration, he did the summation, because here in integration we are treating that it is like a continuous value. Energy is in a continuous fashion. What Planck did that, he treat this particular quantity in the summation form, which can take only some of the particular integer value, e p e divided by summation of p e. So he did this summation, and now generally we are going to derive the formula by some well-known facts. And the thing that I'm going to use here to derive the different Planck's postulate, or you can say that the average energy of each Planck oscillator, which is exactly this particular quantity, is generally from the statistical physics. And I know that you may not do the statistical physics. So after this, in this lecture, you only have to remember the formulas that I will give you of the statistical physics. But maybe in the next video, I will start the series of the statistical physics where I discuss about all of the statistical mechanics. Because in this lecture, Planck postulate, you have to understand some of the statistical physics concepts, like what is the Boltzmann distribution and what exactly all this is. So in this particular lecture, you can only remember the all of the formulas, and in the next few lectures, we are going to study the statistical physics in a whole detailed fashion. So now let's start. So what we have to do. So let me choose some another pen. Okay. Average energy of each Planck oscillator, let's say E, is equals to the epsilon, let's say epsilon is equals to the total energy divided by the number of Planck oscillators. Okay, number of Planck oscillators. So what is number of Planck oscillators? The number of Planck oscillators can be n is equals to, let's say, n0, n1, n2 plus n3, and plus so on, so on, so on, so on. So this is the total number of the Planck oscillators, n1, n2, n3, and 4. But here is a very important general formula that I'm going to show you, and this is exactly from the statistical physics. So you don't have to worry about the particular formula. I will try to make the video on this particular special formula, and that particular formula is generally from the Boltzmann distribution law. So if you were interested, you can start your own learning this Boltzmann distribution law to understand this particular thing. So what was the law is that there is n0, n1, n2, n3, and n4 particles. So what here is n0? What is there n0 means? So n0 means the particles who have zero energy. Zero energy. Maybe there are some of the electrons that have no any type of the vibrations they are doing, and they have the zero energy. Then the particles, let's say here the particles n naught e to the negative r E divided by KT. Okay, so this is the particular formula, and this is R here. Okay, so this is R. So the meaning of this is that how much particle has an energy of, let's say, minus. If you put the value of R as 1, you will get the number of the particles having energy and not into e to the power negative E by KT, where I will substitute the value of E as 1 minute. Let me write this in a more general fashion to understand this, and not e to the power negative R H mu divided by KT. So this is the formula from the Boltzmann distribution, and this formula says that if you have the n naught particles, n0 particles or n0 particles, let's say, who has zero energy, then the particles n1 having another means one increment energy, which is n naught into e to the power negative 1 h mu upon kt is given by this particular formula. So let's say if I want to find out the number of n1 particles, so n1 particle is equals to n naught e to the power negative, putting 1 here, it is h mu upon kt. So this particular relationship generally says that how many particles are in the, you can say that having the integer value as 1, having integer value 2, integer value 3, and all that things. So this is a particular formula which relates that if there is an m naught or n zero number of the particles having zero energy, then the number of particles having the energy as h mu is equals to this particular formula. Then having energy 2h mu, 3h mu, 4h mu is given by this particular formula if you put down the value of nr as 1, 2, 3, 4, and 5. So this is basically the meaning of this particular equation. So by seeing this particular equation, how can I write this particular in a general, more good way is that n is equals to n naught plus n naught into e to the power, sorry, yes, n naught into e to the power negative h mu upon kt plus n2. N2 means number of particles having energy as 2h mu. Because if you remember the formula that E is equals to nh mu. So particles having, if I put the value of integer n as 1, having this particular energy is this, n1. The particle having, if I put the value of n as 2, have this particular energy, n2. Particles having energy 3h mu is here, n3. Okay, so this is exactly the meaning of this particular formula. Nr is equals to n naught E minus n minus r h mu divided by kt. So this is the meaning of this particular equation. So for n2, it means particle having energy minus, 2h mu is equals to n naught E minus 2h mu divided by kt plus n naught e to the power negative 3h mu divided by kt and plus so on, so on, so on. So here, if I take n naught common, what this becomes? This is 1 plus, and let's say here I'm as an assumption that e to the power negative h mu divided by kt is equals to y. Okay, so it means this is equals to y. Then this particular quantity is equals to y square. This particular is y cube and plus so on, so on, so on, so on. Okay. So if you have studied some of the geometric series, how I can write this particular series? So the simple form of this particular series can be written as n is equals to n naught divided by 1 minus y. So this particular series can be written as this particular fashion. Okay, 1 divided by 1 minus y. Now we have evaluated the total number of the Planck oscillators. Now calculate the total energy of the Planck oscillators. So total energy of the Planck oscillator is like total energy is equals to, there are particles n naught having zero energy plus particles n1 having h mu energy, particles n2 having 2h mu energy, particles n3 having 3h mu energy, particle n4 having 4h mu energy, and so on, so on, so on, and so on. So if I substitute h mu as epsilon, it's like E is equals to, and if I put the value of n1 as n naught e to the power negative h mu divided by kt, using the formula that I've discussed now, plus into 1 minute mistake here. 1 minute. Okay, here h mu factor plus n naught e to the power negative 2h mu divided by kt into 2h mu and plus so on, so on, so on, so on. So now what I can write it here as, if I take n naught common, and again if I substitute e to the power negative h mu upon kt as y, it is n naught y and h mu as e epsilon plus n naught y square 2 epsilon plus n naught y cube 3 epsilon and so on, so on, so on. Now, the energy, total energy is equals to, if I take n naught and epsilon common, it is equals to y plus 2y square plus 3y cube and plus so on, so on, so on. And if you remember, this particular series can be written also in a compact manner as total energy is equals to n naught epsilon y divided by 1 minus y whole square. So this is the, we can write this particular expression in this particular compact manner. Now we have both the total energy of the Planck oscillator and the number of the Planck oscillator. So how we can find out the equal or average energy of this particular Planck oscillator? So let's find out the average energy of the Planck oscillator. Remembering this particular formula is very important. And here, this particular formula is very important. So if you remember the formula, then the average energy, epsilon, here average energy sign is equals to total energy divided by n. So if I substitute here n naught and epsilon y divided by 1 minus y whole square into 1 minus y and divided by n naught. Okay, so this is generally the formula. Now what you can do, that you can cut out n naught and n naught. This can be also. Then how you can write this particular equation? It is epsilon y divided by 1 minus y. This is equals to an average energy of the each Planck oscillator. So average energy of each Planck oscillator is equals to putting the value of epsilon as h mu and y as e to the power negative h mu divided by kt and divided by 1 minus e to the power negative h mu divided by kt. So we can also write this particular expression in a more simpler form. How? So like this, it equals to, if I take e to the power negative h mu upon kt on this denominator side, because there is a negative sign, sorry, because there's a negative sign, how I can write this particular expression? So this particular expression can be written as h mu. This is equals to e to the power h mu divided by kt minus, if I take here in denominator side, this and this will correspond to 0 and e to the power 0 is equals to 1. So this is our very important formula. This is the very important formula of this Planck oscillator average energy. Planck oscillator's average energy. And now we are going to also derive this Planck radiation law. How we can derive the Planck radiation law now? So it's very easy. From the basic principle, we can derive now the Planck radiation law. Because the only problem was in the equipartition theorem. We have calculated the number of standing waves per unit volume and we have just multiplied it with the average energy so that we can get the energy density in a given frequency range. And now what we can do is that we have now the average energy in a very good fashion for the also high frequency. And now what we only have to do is that is just multiplying both the terms, which is the number of standing waves per unit volume and the average energy expression that we have just derived out. Now let's write out down the expression for the number of standing waves per unit volume. So the number of standing waves per unit volume, you all know that what it is, number of standing waves per unit volume in a given frequency range per unit volume, given frequency range is equals to 8 pi, okay, 8 pi mu square d mu divided by c cube. And now how we can derive out now the energy density. So energy density in a given frequency range, energy density is equals to our per unit number of standing waves in a given frequency range per unit volume and multiply it with the average energy expression, not kT, because kT is not now valid for the high frequency. We have to write down this particular equation, this average energy expression, h mu divided by e raised to the power h mu upon kT minus 1. And then we will get our general expression for the Planck radiation law. So finally, the Planck radiation law for the energy density given frequency range is equals to 8 pi mu square divided by c cube into h mu divided by e to the power, divided by e to the power h mu divided by kt minus 1 into d mu. And writing in a structured manner, the energy density in a given frequency range is equals to 8 pi cube frequency mu cube c cube h divided by e to the power h mu divided by kt minus 1 into d mu. Okay, so this is your general formula of the Planck radiation law. And this is the one and all formula which is applicable for both low frequency and high frequency. So you don't need to worry to use whether the Rayleigh-Jeans law or the Wien's displacement law, because Wien's displacement law is for the high frequency and this Rayleigh-Jeans law is for the low frequency. Now we have for both and in a single formula, which is the Planck radiation law. Here I am writing in a more good fashion. Okay, so this formula can be written as 8 pi mu cube h divided by c cube into 1 by e to the power h mu divided by kt minus 1 d mu. So, okay, this is your final formula of the Planck radiation law, which is for both the high frequency and the low frequency. But if someone asks you to derive the Rayleigh-Jeans law, it means how I can derive the particular Rayleigh-Jeans law, Rayleigh law from the Planck radiation law. And Rayleigh law is for the low frequency. So for the low frequency, E h mu upon kt. How I can write this? So if you remember the exponentials, how I can write the exponential series e to the power x in the number form is a series which can be written as 1 plus h mu upon kt. I'm not taking the another more term because the Rayleigh-Jeans law is for the low frequency. So for the low frequency, only the first term is required, not the other terms of the expression of e to the power x or whatever your quantity is. So if I substitute this particular e h mu upon kt as 1 plus h mu upon kt for low frequency, see how it transforms into the Rayleigh-Jeans law. So just plug on the value, we will get the Rayleigh-Jeans law. So this is Planck, okay. This is not really Jeans law. This is Planck's law. This is Planck's law. Planck's law. And how I can derive the Rayleigh-Jeans law from the Planck's law. This is the meaning of this. So now the Rayleigh-Jeans law can be derived as U mu d mu is equals to the 8 pi mu cube h by c cube. And here, if I put down the value 1 and negative 1 will cut out. Here in the denominator, you have h mu, and here you have in the expression kt d mu. And this h and h will cut out. This mu and this 1 mu will cut out. So finally, if you write this particular expression, energy density in a given frequency range is equals to 8 pi mu square. 1 minute. 8 pi mu square kt divided by c cube, sorry, divided by c cube d mu. You know what this is? This is the Rayleigh-Jeans law. It is for low frequency. Our equation, your Planck radiation's law, converted into the Rayleigh-Jeans law. So this is all about the Planck radiation law and the Rayleigh-Jeans law. But remember, the statistical physics is very much more important while deriving this particular quantity, because as you can see that I made an assumption here while deriving the deriving this Planck radiation law, which is this particular law, which is the Boltzmann distribution law. So how we can derive this and all that things we'll discuss in the Maxwell-Boltzmann statistics and then the quantum statistics. Quantum statistics is not very much more important, but yes, it's also very important when you are dealing when we have some of the quantum nature and all that things. But mostly we are going to use the Maxwell-Boltzmann statistics in the various places. So this is all about the Planck radiation law. And the next video is soon on going to be statistical physics or whatever physics demand. You can tell me in the comment section that whatever topic you want on the physics, I will try to make a video on that. And maybe the quantum physics can also be there because there is a advanced quantum mechanics, which is the perturbation theory, which is very much more important for the exam purpose and also and all that thing. So maybe we are going to start the perturbation theory next, and also some of the mathematical insights like the advanced version of the differential equations. I mean to say partial differential equations and all that things. These things also come on this particular channel. So hope that you all like this particular video.